In section 3.4, we look at arc length and area of a sector. So first, let's talk about arc length. We know from our definition of the measure of an angle theta in radians that theta is equal to S divided by R, where theta is a central angle in a circle, S is the arc length, and R is the radius of the circle. And this is how we measure an angle theta in radians. So if we want to know what is the arc length, we can take this equation theta equals S divided by R, and we can solve for S by multiplying both sides of the equation by R. Isolating S, we get S is equal to R theta. So the formula for finding an arc length is you simply take the radius of the circle and multiply it by the central angle theta. The key point here, though, is theta must be measured in radians. So if you're finding an arc length and you only know theta in degrees, you have to convert it to radians before you use this formula. Let's take a look at this example. Give the length of the arc cut off by a central angle of 2 radians. Okay, so they're telling us that the angle theta is 2 radians. I'm just going to write 2. And this is in a circle of radius 4.3 inches. So the formula says the arc length is equal to R times theta. So we take the radius R, which is 4.3 inches. We multiply it by theta, which is 2. And this gives us 4.3 times 2, which is 8.6. And notice that we still have inches left over. So the length of the arc in this case would be 8.6 inches. This is a very straightforward problem because the angle they gave us was already in radians, so we didn't have to do anything except multiply R by theta. In the next example, they ask us to find the length of the arc cut off by an angle of 45 degrees in a circle of radius 2 centimeters. Okay, so the key point here is we cannot use 45 degrees. So our angle theta, which is 45 degrees, needs to be converted into radians. Now 45 degrees is a special angle. So 45 degrees we should know is equal to pi over 4 radians, right? And again, we don't have to write the RAD here. And we know that R is equal to 2 centimeters. So the arc length in this case, S, is equal to R theta. This is equal to 2 centimeters multiplied by pi over 4. And if you do the math on this, you get 2 pi over 4 centimeters. Reducing, this is equal to pi over 2 centimeters. So this is our exact answer. And then if they want a decimal approximation, you could then plug this into a calculator, just take, pi divided by 2, and that would give us approximately 1.57 centimeters. So again, theta must be in radians if you're going to use this formula. Let's look at example 3. In this problem, we're told that the minute hand of a clock is 1.2 centimeters long. To 2 significant digits, how far does the tip of the minute hand move in 20 minutes? Okay, so let's imagine we have a clock. And for simplicity, I will position the minute hand pointing directly upward, vertical. And the length of that minute hand is 1.2 centimeters. And we want to know how far does the tip of that minute hand move in 20 minutes. Well, since it's a minute hand, in 20 minutes, the hand will be positioned over here, roughly. And we are trying to find how far the tip moves. So we are looking for that arc, S. Well, we know the radius is 1.2 centimeters. The question is, what is theta, right? Because there's an angle theta associated with that movement. Well, on a clock, 20 minutes, if you divide that by 60 minutes, you get 1/3. So on a clock, 20 minutes out of 60 minutes is 1/3 of a revolution. So the angle associated with that is going to be 1/3 times the angle value of one revolution. Well, one revolution is 2 pi. So 1/3 times 2 pi is 2 pi over 3. So that's the angle we need to use here. And now the arc length, in this case, is S, again, is equal to r theta. This will be 1.2 centimeters multiplied by 2 pi over 3. And then now we just have to do the math. And for this, you can simply multiply 1.2 times 2 pi and then divide it by 3. You can plug all that into a calculator. And in the end here, we get 2.51327 and so on. And that's in centimeters. And if we're rounding to 2 significant digits, that means we're rounding to right there. And so this is approximately equal to 2.5 centimeters. So this next example is just for fun. It says figure 4 is a model of the Ferris wheel known as the Riesenrad. The diameter of this wheel is 240 feet, and one complete revolution takes 16 minutes. The bottom of the wheel is 12 feet above the ground. Angle theta is the central angle formed as the rider travels from point P0 to point P1 on the wheel. And over here we have a demonstration. So P0 is the point at the very bottom of the Ferris wheel. And as it begins to move, the rider moves to point P1. We want to find the distance traveled if the angle theta, so this angle here, is 30 degrees, 90 degrees, and 135 degrees. Okay, first of all, we need the radius of our Ferris wheel. They tell us that the diameter is 240 feet, and one thing we should know is that the radius is equal to the diameter divided by 2. So 240 feet divided by 2, that gives us a radius of 120 feet. After that, we need to compute the arc length, right? Because we're looking for the distance traveled here, and that distance traveled is just an arc length, S, right? And S is given by r theta. So to do this, we have 3 different values for theta we're going to use: 30 degrees, 90 degrees, and 135 degrees. But we have to convert each of those into radians. So for the first one, we're going to have theta equals 30 degrees, which is pi over 6. For the second one, theta is 90 degrees, which is pi over 2. And finally, we have theta equals 135 degrees. And if you convert 135 degrees into radians, you get 3 pi over 4. And for all of these, we use the radius of 120 feet. So I will set up all of these problems simultaneously, and we'll go ahead and do that here. So for the first angle, the arc length is going to be r, which is 120, multiplied by theta, which is pi over 6. For the next one, we do the same thing. Radius is 120, multiplied by theta, which is pi over 2. And finally, we have 120 multiplied by 3 pi over 4. And for this, you can actually get exact values So when you multiply 120 by pi over 6, 6 goes into 120 20 times. So you can actually cancel the common factor there and get 20 times pi. And that would be in feet. So that's our first answer. For the next one, we can divide 2 into 120, which goes 60 times. So in this case, S will be 60 pi feet. And finally, for the last one, we can say 4 goes into 120 30 times. And 30 times 3 is 90. And so we end up getting 90 pi feet. And so these are all of the exact values. But I think what they wanted was approximations as well. And actually, they don't ask for approximations, but let's go ahead and give them anyway. So I'll plug each of these answers into a calculator, and we'll do 3 significant digits. So 20 pi, if you do 3 significant digits on that, rounds to 62.8 feet. And then 60 pi, if you do that one, you get S is rounding to 188 feet. Again, that's 3 significant digits. And 90 pi, if you plug that in to your calculator, you get 283 feet, approximately. So these are the approximate values for each of those. Now, there's an interesting application of arc length when you have a central angle that is very, very small. So let's focus in on this diagram right here. In this diagram, we have a very small angle such as 1 degree. And this is actually very exaggerated. 1 degree would look smaller than this if we actually drew it according to its size. But let's suppose you have a central angle of 1 degree and you're on a circle. So you have an arc out here, which is on that circle. And then you can also draw the chord, right? So we have the arc from point A to point B. And then we have the chord AB, which is the straight line segment drawn there. What I want you to notice is that the length of the chord and the length of the arc are different, but very close to the same measurement, okay? So for really small angles, you can use the length of the arc to approximate the length of the chord. Now let's see about how that would apply to a particular problem. So in this problem, we're told that a person standing on the earth notices that a 747 jumbo jet flying overhead subtends an angle of 0.45 degrees. If the length of the jet is 230 feet, find its altitude to the nearest 1,000 feet. Okay, so a person is down here. As they're looking up from the front of the plane to the back of the plane, they notice that that angle is 0.45 degrees, which is a very, very small angle, and that's because the jet is presumably very high in the sky. The length of the jet is 230 feet, and we want to approximate its altitude. Okay, the altitude of the jet would just be the distance from the jet straight down to the ground. Okay. Now, we already know that the arc length from A to B is approximately equal to the length of the jet because of what we said over here. The length of the chord is very, very close to the arc length for very small angles. So the length of this arc AB, we can assume, is very close to 230 feet. So I'll label that now. S is approximately equal to 230 feet. Now, why do I care about that? Well, we know that S is equal to R times theta. In this problem, we know what theta is, right? Theta is our angle, which is 0.45 degrees. And we know what S is. S is approximately 230 feet. And so we can use that to find R. So if I divide both sides by theta, R is equal to S divided by theta. So let's go ahead and figure out what R is. In this case, R is going to be S, which is 230 feet, divided by theta. But remember, theta must be in radians. So I have to convert that real quick. We know that theta is 0.45 degrees. I have to multiply that by pi over 180 to convert it into radians. And you can do this exactly, but I think for this problem, I'm just going to use a decimal approximation. So if you take 0.45, multiply by pi, and then divide by 180, the angle theta is approximately 0.0078539. And I'm rounding to lots of significant digits here because I still need to use that to calculate something else. And I don't want to round it to be too short of a number here, right? I need to maintain more of my significant digits since I still have a calculation to go. So now when I go to figure out R will be 230 divided by this value of theta. And if we do the math on that, 230 divided by that answer is approximately equal to 29,284.5. Okay? All right. Now, that value of R, if you approximate it to the nearest 1,000 feet, would be 29,000 feet. Okay? That's what they tell us to do here. But R is not what we're looking for, right? We're looking for the altitude of the jet. We already said the altitude was the distance from here straight down, right? So I can call that H for height. But here's the thing. When this angle is very, very small, R and H are very close to the same value. R is approximately equal to H for really small values of theta. So this means that the height is also approximately equal to 29,000 feet. So don't lose any sleep over this example. It's just here to show you that when you have really small angles, the length of the chord is approximately equal to the length of the arc. And this segment right here, which you can think of as the altitude, is very, very close to this sort of hypotenuse of the triangle. All right, let's move on to sectors. So first, what is a sector? Suppose we have a circle of radius r and we have a central angle theta. We already talked about this arc has a length, which we call arc length. Well, if you cut this little piece out of the circle, this is what we call a sector. So the question is, what we want to do here is figure out what is the area of something like this. Well, it's related to the area of a circle. So we know that the area of a whole circle is pi r squared. So the area of your sector is going to depend on how big your angle is, right? Because if your angle is larger, you're going to have a greater portion of that circle. And if your angle is smaller, you're going to have a smaller portion. So what portion of the circle do we have? Well, what you do is you take your angle theta and you divide it by one full circle, which has an angle of 2 pi. This is going to be the ratio or the portion of the circle that you have when you have a central angle of theta. So the area of the sector, you're going to take that portion of the circle, theta over 2 pi, and you're going to multiply that by the area of the circle, which is pi r squared. When you do this, the pi's cancel out, and if you rewrite this formula, you end up getting a equals 1/2, and then theta times r squared, but we usually like to say r squared times theta. So that is the area of a sector. 1/2 times the radius squared times the measure of the angle theta. And once again, theta must be in radians. Very important. Okay, so let's take a look at a simple example here. Find the area of the sector formed by a central angle of 1.4 radians. So that's our theta. And the radius is 2.1 meters. So the area of this sector is 1/2 times the radius, 2.1 meters, quantity squared, times theta, which is 1.4. And this can all be plugged into a calculator simultaneously. So if we do 0.5 times 2.1 squared times 1.4, calculator tells us this is 3.087. And now the units are going to be meters squared because you are squaring these meters. Okay? So our answer here is 3.087 square meters. I prefer to write it using the exponent notation, but both of these are good. All right? Now, technically, they only gave us 2 significant digits. So if you really wanted to round this, you would say it's 3.1 square meters. All right? Pretty straightforward, though. So the important thing here, of course, is you have to know the formula. Next example, if the sector formed by a central angle of 15 degrees has an area of pi over 3 centimeters squared, find the radius of the circle. So we're talking about a sector, and it tells us about an area. So we know we're going to use the formula A equals 1/2 r squared theta. But in this case, they're asking us to solve for r. So what I could do is just solve for r in the beginning. So to do this, I can simply multiply both sides of the equation by 2. Doing this will cancel the 2's here, and we get 2a is equal to r squared theta. And then I can divide both sides by theta. And doing this gives us 2a over theta is equal to r squared, as these cancel out. And then now to solve for r, I just need to take the square root of both sides. And when I do that, I get r is equal to the square root of 2a over theta. Okay, so if I know the area of the sector, and if I know the central angle, I can find the radius of the circle. So now let's plug in the information that they told us. So they told us the area of the sector was pi over 3 square centimeters, and they told us that our angle was 15 degrees. But once again, you have to remember that we cannot use angles in degrees. It has to be in radians. So we have to multiply this by pi over 180 to get this in radians. 15 goes into 180 12 times. So theta is pi over 12 if you want to put it in radians. And we have to put it in radians. So now we can get the radius of the circle by taking the square root of 2 times the area, which is pi over 3, divided by theta, which is pi over 12. This is the square root of 2 pi over 3 divided by pi over 12. And I'm going to flip and multiply. So we have 2 pi over 3. Instead of dividing by pi over 12, I'm going to multiply by 12 over pi. And now if I cancel, we can say the pi's cancel out. 3 goes into 12 4 times. And what I have left over there is the square root of 2 times 4, which is the square root of 8. And the square root of 8 is 2 radical 2. Now, also we had units in here. The units were centimeters squared, so my apologies for that. When you take the square root of centimeters squared, you get centimeters. So the radius of this circle must be 2 radical 2 centimeters. And if you want, you could plug that into a calculator. 2 radical 2 is approximately 2.8 centimeters. So just pay attention to whether they ask you for the exact answer or if they ask you to approximate it. In our last example, we are told that a lawn sprinkler located at the corner of a yard is set to rotate through 90 degrees and project water out 30 feet. Okay, so we have a corner of a yard here, which is 90 degrees. They tell us that. And we have a sprinkler spraying water a distance of 30 feet. And it's going to rotate, as sprinklers do, back and forth like this. And as it rotates, it sprays water 30 feet and it covers this whole area. So we want to know to 3 significant digits what area of lawn is watered by the sprinkler. All right, well, for this problem, we have the radius is 30 feet. The angle theta is 90 degrees. We cannot use 90 degrees, so we convert it to radians, which is pi over 2. And then the area covered is 1/2 times r squared times theta, which for this problem is 1/2 times 30 feet quantity squared times theta, which is pi over 2. Do the math. This is 1/2 times 900 square feet times pi over 2. And this is 900 pi over 4 square feet. And if you divide 900 by 4, you get 225 pi square feet. So that's the exact answer. And then to get a decimal approximation, we can just plug that into the calculator. 225 times pi is approximately 707 square feet. And that's to 3 significant digits. So the calculator displayed 706.858. So when I round that to the 3 significant digits, it changes to 707.